Hello, it's David. Now, at the end of part 2 of this Falcon motherboard restoration series, I had a working motherboard only in the sense that I could boot up to a diagnostic cartridge and run some tests, and things appear to be going pretty well. We still had some outstanding issues that we needed to address. Notably, there was still a problem with the DSP. There's a flip-flop that we removed at the tail end of last video, which I need to reapply. And I was running into failures on the bus arbitration logic, but that's because we had hardwired a bus grant signal. So we're going to try and address those in this video and see how far we can get to getting this machine up and running. So I think first things first, let's have a look at that that flip-flop chip, which was U40. It's had its little soak and a bit of a scrub up. And it's got nice widely spaced legs, so this should hopefully be a relatively straightforward process to get it back on there. Bringing in my preferred SMD K-tip here, 290 degrees, because I'm using my leaded solder. And we'll get ourselves a blob. That was silly. There we go, the alignment looks about right there. So because these legs are quite widely spaced, I don't have to worry about too much solder really. So we'll put a generous blob on here, something like that, and try and get one of these pins anchored down. There we go. And then the second side, despite, I don't really want to spin the board around, so despite the slightly awkward alignment, this should be easier because now the chip is anchored to the board. Similar thing, big old blob on the end of the tip here. Okay, so here we go. This is how it looks after the cleanup, and I think that's pretty good. I can't detect any shorts between the pins that ought not be there. Most of the ones at the top are connected to ground, so that's fair enough. So I'm happy with the repair there. However, we still have two obvious faults still on the diagnostic cartridge. This is the first one. This is the digital audio section test, and some of this isn't going to work because there's no loopback attached, but this one's key, not executing program, and a second one here, SRAM test timeout. So that's basically telling me that the DSP is not working at all. Second one that's failing is the obliter test here. Nothing's going to change there. That's going to stay sat on the blue screen, and you can see on the LED down here the first light has gone off, which indicates that we are no longer in control of the bus. Now I'm fairly sure that second problem we've just seen with the obliter failing and the bus never being properly relinquished is down to the way that we hacked up the bus grant from the missing CPU in the first episode there. So I think I'm going to turn my attention to that in a second. The initial problem that we've just seen there with the DSP is almost certainly caused by the damage done here to the bottom end of this chip. Now I don't know how easy this is to see on here because the shadows aren't great, but at least one of these pins is mobile. There we go. Did you see that? That pin moved. Now that's the one with the bare trace underneath it, and that is actually crooked. So I'm not surprised that that's not working. The one next to it doesn't appear to have a pad to connect to, and I think that is supposed to be an address trace. So that one is probably in need of repair, and certainly I'm going to have to do some straightening and buzzing out of this one, get that reattached there. My suspicion is that that's had some kind of modification pinned on top. I can't imagine what it is. I don't think you need to do anything special to like accelerate the DSP chip. That crystal there, I think, is probably all you need to change. So I'm a little bit confused as to what's going on there. But I think we can say that DSP is unlikely to work for the time being. This is the SRAM here that it was failing the test. And, well, again, it doesn't surprise me if the address line is actually just, well, has no pad to connect to. So I think we'll turn our attention away from the DSP for now, because we can always make ourselves a copy of Emitos that won't require the DSP on initialization in order to get the board up and running. So I think I'm going to go back and have a look at the bus mastery logic. There's that little modification that I made in the first episode. This is just a, what is that, 100 ohm resistor, I think. Oh no, actually I think that might be a 10k. It's something a bit dramatic, perhaps not ideally suited, but just connecting the bus grant, the internal bus grant signal to ground all the time. Just pulling it low basically. Well, this is interesting and not what I was expecting at all. This is just a bit of a hack, and I tried it just for shits and giggles. What I have here is the bus grant, the 030 bus grant pin here, wired through my decade resistance box over here, set to 1 kilo ohm, and just going straight to the bus request pin up here. So when bus request is asserted, it pulls the bus grant low via a 1k resistor, and that seems enough to pass the blitter test. Allow me to commend to you the sponsor of this video, PCBWay. Now, as the name suggests, they are a PCB manufacturing company, but they also do PCB assembly, PCB design consultancy, sheet metal fabrication, CNC machining, 3D printing, and they have an extensive library of shared projects contributed by their users. There's also a module store where whole items can be purchased pre-made. If you think any of these maker-centric services could be of interest to you, please do have a look at their website. I thank them very much for supporting my work. So I was expecting a rather more complicated workaround than that, but if this gets me to the point of seeing the Atari boot screen on toss, I'm just taking out the cartridge now. That's been removed, and we'll throw the switch. If this gets the Atari boot screen, which does use the blitter, that, well, there we go. Look at that. Then this actually could just be a quite quick modification I can do to the back of the board. Put a 10k resistor between the bus grant and bus request pins. I'm pretty sure this isn't meant to work. I'm not entirely sure I know exactly how that's working, but providing the blitter doesn't step all over, or other DMA, you know, there's floppy disks and stuff, nothing's connected also at the moment. Providing that doesn't step all over the 030, because it's basically being granted. Here we go, we've got the B coming up. Provided it doesn't step all over the 030 when bus mastery changes, well, fine. I mean, then that's a really short, look at that. That's a really short and quick workaround. Ladies and gentlemen, I give you a Falcon030. Right, I'm gonna turn that off. I'm gonna solder a resistor across the back of that, and we'll see if that's sufficient to get things to work. Wow. I'm not even going to pretend this is going to be in anyone's top 5 neatest looking bodge wires ever. But there's a 1K resistor down there, and there is a bodge wire going up from the bus request line on the expansion port down there to that internal bus grant line. So yep, let's just measure that out. So pin 4 of U68, pin 16 if I can count it, 2, 4, 6, 8, 10, 12, 14, 16. 1 kilo ohm. Let's give it a try. Okay, power back on. Green light, Atari logo. Should be 4 megabytes of memory. Let's might as well let it finish. It's pretty quick. Yep. Now there is no floppy disk attached. There is no hard disk attached. I've got an IDE on here. We've got the floppy, but I don't think I've got a drive. Ooh, I've got a blue SCSI. I can always try the blue SCSI, and in fact the blue SCSI uses DMA, which so does the Blitter. The fact that all these menus are drawing indicates the Blitter is working. Beautiful full screen VGA picture. Let's put in the blue SCSI. Right, so this is the slightly Frankenstein's monster setup I've got going here. So there's the blue SCSI in the back with my existing partition in there. I've nicked the Gotek out of my working Falcon, so we've got that there in order to get drivers and test software, what have you, onto that partition. So that's just floating around here at the front for now. Haven't got the driver disk in. In order to stop using the other Falcon's keyboard, I've got this slight monstrosity in here. This is my little homemade adapter for the keyboard port, going off to an RJ45 to RJ12, is it, adapter, and the Mega ST keyboard over here to provide input. Right, so I'm going to boot the Falcon up to the desktop, and then we'll put in my HD driver disk, which is on one of these little USB dongles here for the Gotek, and we will try running it from the desktop and see what we pick up. Right, so I'll put the floppy in the virtual floppy in the drive. This has got HD driver 1114, I think, on it. There we go. Well, so first of all, this is a good sign. This is the first mass storage that we've seen attached to this machine that works, which to me suggests that probably that DMA chip is behaving itself and our bus arbitration is working. Admittedly, this is only a 25K file. I think we need to see something over 64K, which is sort of the, you know, the typical buffer size that gets used. But we will we'll give this a go. Right, here we go. Ah, right. So, ooh. Well, that flashed on the screen pretty quickly, but I did see blue SCSI, Pico, I think, in there somewhere. But I also saw some gibberish, so we'll have to keep an eye on that. So we might have some problems here. Let's install devices. Well, there we go. It's found some hard disks, and there we are. There we go. That is actually the contents of this disk image that I have here on the blue SCSI from the last time I used it. It's got a copy of Mint because I was using Basilisk. That's right. I was using Basilisk off here. There it is. Yeah, we've got Basilisk over on drive D. Well, that won't work until I get the AltRAM working on DFB1, but this machine should be technically capable of running that eventually. Okay, so this little escapade with the Gotek here, with HD driver in there, the blue SCSI at the back, this shows that basically the work that we've done there on that chip, that's the SDMA chip, and that's responsible for both floppy and SCSI accesses, that the repair work we've done on that has obviously worked. And because that requires bus arbitration, that strange little mod that we did on the bus grant line also seems to be sufficient to allow this stuff to work. Well, my good mood has unfortunately been punctured slightly. I've started seeing this error with the diagnostic cartridge. Once or twice while I was rebooting, I just in normal TOS mode, I was seeing a message about a CRC error on the ROM, which didn't make much sense. Let me just take that diagnostic cartridge out and we'll try booting up normally. We're getting no sync signal here. I'm pressing reset and it's not getting into sync now. So yeah, our lights here are behaving as they ought. You know, it appears to be trying to run things from ROM. The clock's pulsing away. Address strobe's working. We appear to have bus control, but yeah, we're getting no sync on the VGA signal. If I switch it across to RGB, okay, the power comes on there, and yeah, I'm just getting a black screen on the RGB output as well. So something has happened. And just for completeness, yeah, there we go. We're getting the same message on the RGB output when we put the diagnostic cartridge back in. So I'm not sure what could cause that sort of error message, both on the normal onboard ROM and also the diagnostic cartridge. If it were a data line error, you wouldn't expect much in the way of code execution at all. If it's an address line error, how does it got to the point where it only seems to affect the calculation of the checksum or whatever it is that it does to identify those versions of the diagnostic cartridge? So that's a little bit confusing. So putting that to one side, let's turn our attention to what we know still doesn't work on this board. And the most obvious candidate here is the DSP. We've seen it fail the diagnostic tests. It has a loose pin. We know that for a fact. And obviously it's a bit of a mess. Do I start patching up the DSP in the hope that that's the trick? Or could it potentially be something else that's maybe easier to assess? And the other one that crossed my mind, going all the way back to part 1, is down here, right at the front of the board, this NVRAM replacement. Now, I don't think there's anything wrong with the NVRAM replacement itself, and we did actually conclude, possibly a little bit prematurely, that this was working fine and was holding on to the settings. It turned out when I powered it on the next day, just before actually all of these problems showed up, that we were back to the default settings. So it's possible that that battery actually is dead, and perhaps I should whip that out and give that a bit of a measure. Okay, so what about the voltage on this battery? Okay, 1.04 volts. Yeah, I think that's normally a 3-volt battery. It's probably 3.2, isn't it? So yeah, probably that battery is in need of replacement. Let me see if I've got one of these. This is a CR1220, which means 12 millimeters diameter and 2.0 millimeters thick, I believe. Right, so these are actually two different approaches to the same problem. This is an Exos board, that's Exos's logo there, using a modern chip with the button cell there on top. This is an original Dallas chip with one end cut off. The chip's sort of, only the bottom half, and it was the battery that was on the top, and the old battery cut off, and a new coin cell mount put on place. But they basically do the same job. And as luck would have it, I have one 1220, brand spanking new 1220. So we can pop this out of here. We can try this one. We can try this one. See if it makes any odds. 3.3. Perfect. Right, well, if I can keep my capture card alive long enough to actually capture this, let's give it a go. Right, so we've got the new NVRAM in. We are seeing execution going here. And it's booted properly. So maybe it was that. Gosh, maybe that was it after all. Okay, so maybe we did the right thing by not going straight to the DSP. Let's run, we've got a clock, there we go. Real-time expansion, diagnostic, let's have a look. Testing RTC. Pass. my time and date are wrong. Green. Okay, so diagnostic card is removed, power back on. And there we go. Now it's got the logo. I've taken out all of my peripherals. There's no floppy and there's no SCSI in the back. But that should let us boot to desktop. Shall we set that real-time clock date? That might be the plan, mightn't it? I've got the Falcon language disk on here somewhere, I think. Okay, so here is the control panel. So I'm going to set a time of 22:31 on 01:09:25. There we go. Sorry, I hadn't realised that actually the borders were off the off my capture range. But there we go. I've got that set up and that's ticking away. And I think given the lateness of the evening, I am going to call that a day, and we'll come back tomorrow and see whether that has remembered the time and date. Well, it's the next day and we've got everything set up again. Let's boot the language disk and we'll see whether we have remembered any of those settings. Well, the only setting I changed, I think, was actually the date time. I can see it's still booting up in ST low. So I haven't yet actually configured the boot settings. Okay, so we're 21:22 on the 2nd of September. 21:21 on the 2nd. That's good enough for government work. Let's set that a minute ahead. Perfect. Excellent. Right. I want to test the audio. This is just worth noting. I'm still seeing this problem where sometimes, there we go, it's just worked this time. I was getting a white screen. Sometimes on reboot, soft reboot, there we go, look, I'll just get a white screen. Now, you'd think perhaps this is frozen, maybe it's something to do with the bus arbitration. But the keyboard still responds. I'm still rebooting this via the soft reboot option. I can still use the reset switch at the back here, or via the keyboard. So it doesn't look like that particular problem was caused by the NVRAM chip here. There's a cold boot where it's wiped the memory, so that could be something else. I know that the IDE is still showing up as a problem, and we know we haven't fixed the DSP yet. So let's just power that down, bring that back up, and if it boots this time, I'll talk you through what I've done. No, you see, look, still no Atari logo. Is that a problem with DFP1? Yeah, but what then? Why would... I mean, code must still be executing because, like I say, the Control-Alt-Delete works. No, it's a bit peculiar. There we go. See, I'll leave it powered down for a few seconds and we get our screen back again. So let me just explain what I've done here. I've got my blue SCSI in the back, and I'm booting off that at the moment. I've got just a small partition in there that I've put a boot sector on. And as you'll see this flash up the screen here, that's interesting. IDE actually said no device there, which that is promising. Often that shows gibberish, which to me, given that the IDE bus is pretty much across the data bus, it's difficult to know exactly what could possibly be the cause of that. Anyway, what I want to do first of all is just test our sound. The reason why I'm interested in the sound is we've got a codec chip in here, and we've done some work on the DMA, and obviously there is DMA sound on here. But there's also an AY chip, like on the real on the traditional ST. So we've got both types of sound to test here. No, something in my boot up script has caused the tentacle to fail there. Let's try that again. I see now. There we go. We've gone back to that white screen. Now I suspect that might be related to that DSP problem, because I think in general TOS won't boot up if the DSP is missing. Yeah, look at that. I might be barking up the wrong tree, but perhaps there's something that happens there on a cold boot that lets it get away with it, but then won't happen on a warm. I'm not sure. Anyway, I'm going to hold down Control to bypass loading all of my boot up programs, so that's what I'm doing now. And then as this HD driver image throws up the screen, oh good, it's still saying no device for IDE as opposed to gibberish. And we'll just run Day of the Tentacle here with a completely vanilla system. Now hopefully the audio capture, I've got a cable in the back here, hopefully the audio capture will work. I could hear something. The reason why Day of the Tentacle is nice is because it uses both the AY sound chip and samples. You hear that? That plop plop, the fish, that's DMA sampled audio coming through the SDMA chip there. As is the coughing bird. And there's music in the background. And that music comes from the AY chip.
I'm thirsty. I don't think you should drink that.
But anyway, to me that sounds great. You can hear the sampled music there. Sorry, the sampled oh gosh, can't see the cursor. There we go. So I can turn off the DMA sampled sound effects there and just have the Atari YM music still going. Now it's a lot quieter, and I think that's actually a bug with the Falcon, that the levels aren't properly matched. But I can even have the YM sound effects. I've got the music volume turned up to maximum there. Yeah, you see how much quieter the samples are now. And you can hear how much poorer quality the samples are, because that's obviously now using a programmable sound generator as opposed to actual sampled speech.
He says that purple tentacles mutated into an insane genius.
And definitely you can tell the level difference. But anyway, perfect. I think we can put the sound down as working. Right, so I'm still tempted to avoid the DSP until the end. So my next question is, does that IDE device work? This is the IDE header that has mysteriously stopped producing errors. Now, those are very short pins, I'm going to be honest with you. On a stock Falcon, I think that this is actually a cable that is soldered directly onto the board. On my one, I do not believe you can unplug it. So I suspect that this has been changed, and those pins are very short, which might cause a problem with us plugging things in, but I don't think it would cause a problem that we were seeing with earlier on in the video with those corrupted IDE names. Nor does it explain quite why they've gone away. So I think what I'm going to do is going to bring in the old contact cleaner and make sure this has a jolly good scrubbing. Because I don't know, I can't really think of anything that would cause the IDE to report there was something there when there wasn't. Other than perhaps some kind of interrupt getting triggered when it oughtn't be. I can't remember if it's interrupt based, the IDE port on the Falcon. Basically, half of these are data lines and they connect straight onto the data bus. So if they were shorted or not working, well, I mean, nothing on the Falcon would be working, would it? This does appear to be another area of the board where there do seem to be some sticky residue. There's something up here. Comes out better on the camera. In fact, are they unpopulated resistors? R33, R32. So perhaps that's all it is. Perhaps it's just a bit of flux residue where there's been some work done. But if that has been changed, they've done a much better job than elsewhere on the board. Let's put it like that. Incidentally, I did have a quick look on the schematic, and R33, R32, R31, those ones around there, yeah, they are footprints for non-modulator systems. So I presume that's basically for the French market. I don't believe that French computers tended to have modulators. So this contraption has been seen on my channel before. This was a prototype board that I made for an auto byte swapping IDE adapter, and I have never gone back and redesigned it to be in a bit more of a compact form factor. So this is my SD card to IDE 44 adapter, regular off-the-shelf component. This is my auto swapping byte order adapter. That means that on this disk I can have PC order partitions and it work automatically as a Falcon device, and then just on a short extension wire here. Now this is my disk for my actual Falcon. I've just pulled this out of the board, so I know this works. I know this even boots. It's got a hard disk driver on it, and I'm going to try and get this onto the pin header here. Does that feel right? There we go. Pin 1 at this end. There's the red line going to pin 1 on the board here. Now this has an activity light up here. There we go. Okay, well that's balanced quite precariously there, but the activity light and the power light should be in shot. And I have removed the virtual floppy disk, so if this is recognised, then the hard disk drive on here ought to boot up. So let's bring in the capture card and we'll give that a try. Power's coming on. There's the red light. So on the screen we should get the memory check. Okay, and as soon as we bypass the memory check, we should see a flash of activity there if it's going to work for us. Yes, green. I saw. Whoa, it's going. That's gone off the screen quicker than I could see it, but that actually booted from that. So that's actually my boot disk from my other Falcon. Okay, right. Yeah, you can see up here that this is trying to run the fast RAM installer, and I think that's probably not working on this this cobbled together old DFB1. Yeah, if the bus arbitration's working, I could probably just put my DFB1X in it. There we go. We've booted up. Beautiful. Yeah, so I don't know what the issue was with the corruption we saw on here, and it could just have been the dirt on the bottom, I suppose. It did kind of go away before this test, so I suppose we haven't proved that we fixed that. Just that it had basically vanished before I plugged this in. But it is a little bit worrying. So I'll need to keep an eye and see if that comes back in the future. Press any key. Yeah, I think that's probably too much memory. Shall we put DFB1X in here? So just by way of an explainer, in case you haven't seen any of my previous videos, this is DFB1. This is a revision 5 board. That was the first release board. Ignore the little piggyback, I've been experimenting. That is what a DFB1 looks like. It's got a 50 megahertz or up to 50 megahertz 030 governed by that oscillator, and it's got an up to, in this case, 40 megahertz FPU governed by that oscillator, and it's got 128 megabytes, 64 or 128 megabytes of fast RAM here on board, and it's also got some onboard ROM. In this particular case, I'm experimenting with an SPI driver, but I haven't touched that for over a year. So that's DFB1. That was, or is, my open source Falcon accelerator that will fit in to your Atari Falcon without any soldering and without the need to remove the PSU, although I do as a matter of course. This is DFB1X. This is a closed source, officially licensed derivative built by Exos and marketed on the Exos store. And this has some modifications to a few things. There's no longer the two oscillators. It's got SMD oscillator on the back somewhere instead of, or down here, sorry, instead of my great big chunky through hole ones. Otherwise, the layout is broadly similar. 128 megabytes only. I think this one doesn't have the option of the 64. And the idea is that the FPU and the CPU have been tested to work at the same speed. So in this particular case, this is a 50 megahertz board, but there's also 40 megahertz boards available. The main difference between this commercial version and my open source version is that this one, obviously, well, sorry, there's two main differences. One is technical and one is not. The technical one is that this one requires the onboard ROM, which is hidden under this memory card here on the Falcon, to be removed, because the ROM here is actually accessible by the motherboard and is fast ROM. That's a downside. That has a downside. Not one that I particularly am keen on, so my boards don't do that. But that's the one technical, or the main technical difference. The main other difference is, of course, that it is commercially supported. Mine, very much a case of you get what you get and you don't get upset. You are the frontline support for my open source version. So let's pop this one in here. The other thing we need to do is remove that ROM. Oh, and just for completeness, the board that we've been using was a DFB1 revision 4. This was the last development board, if you like. You can see it's got some bodge wires all over it where I made mistakes, but otherwise it shares broadly the same layout as the production version. But I was expecting to have to do some jiggery pokery with the bus arbitration on the board here because of lack of onboard CPU, and it's turned out that I potentially don't need to do that. So I'm hoping that this off-the-shelf DFB1X will simply work. But what we do have to do is remove the onboard ROM. So that's that under there. It's in a very awkward place. Having to get this board in and out is somewhat of a pain. As is, incidentally, pulling PLCC ROMs. Yep, that's slipped. Oh, damn it. Scratches to the corner of the ROMs there. I'm gonna go in and just do it this way anyway. Right, anyway, memory board back in. DFB1X, commercial off-the-shelf DFB1X, is now in place. That looked positive. Unfortunately, my capture card takes some time. Yes, I was about to say it takes some time to power up, but there we go. Start capturing. And we're booting from the hard disk. Right, now let's check what sort of memory we have available. Okay, still 1.8 megabytes, so it has not picked up the fast RAM. I can't remember if this had an adapted version of the operating system on it. So let's re-enable fast RAM 9. Fast RAM 9, there we go. Which is my preferred version of the fast RAM map ROM combination by Anders Granlund. This just does the RAM and nothing else, doesn't do any clever trickery with ROM shadowing or anything like that. And there we go, we now have 136-ish megabytes of free memory. So I now rather hazard that we can probably run a copy of Doom. And we have an FPU, so we can run the FPU version, hopefully. Now I don't know whether the audio capture works at all. I can't hear anything. Yeah, I can hear something, I think. Oh. Okay, well that seems to have gone round a full cycle this time, and all I did was reseat the memory board. I'd had this out to remove the ROM, and perhaps that wasn't making very good contact because it appeared to be, like you can see a memory test pattern in there when it failed that last time. So I just put a bit more contact cleaner and reseated it a couple of times, and that looks a far more stable proposition now. But anyway, I'm very pleased with that. The IDE appears to be completely functional, so I'm just going to have a go at booting into my Mint environment here. So this is from my drive G, so I'll just have to tap the G key on boot up, and let's see what we get. Okay, so XAAS is loading up, and perfect, there we go. What's I forgot to check how our clock had fared as another day's gone past. Let's open up the clock. 22:21, perfect, and the date is now backwards, but the 3rd of the 9th. So yeah, the NVRAM now seems very happy. Quite pleased with that. Gem Bench is not particularly multitasking friendly, so I'll close all the other windows, and I'm just gonna, I think, let that have a full run. So just having a glance down there, bear in mind this is a multitasking environment, so it's no surprise that the RAM and the ROM access are slower. Blitting is a lot slower than usual because we're not actually using the blitter chip. That's what NVDI replaces or stops being used, basically, and that's fine because, well, first of all, we're not in 16 colors, we're in 256 colors, and that will make a bit of a difference. And a lot of these graphics figures are, to be brutally honest, purely down to NVDI. This is the key one that I'm interested in. Integer division of 311%, 1.82 seconds. 311% from 16 megahertz will get you to 50 megahertz, which is what we're running at. And that is pretty much unaffected by the multitasking. So I must say I'm very pleased with that, and let's have a quick review on where we are with this board. So we've checked all the gals and we have switched them over and we're happy with those. We're not using the FPU socket because there's no onboard CPU, so that's irrelevant. The DFB1X, which is an off-the-shelf commercial version of my booster, works in here with no further modifications after we've done that bus grant hack, so I'm perfectly happy with that. The NVRAM down here has been changed, or the battery has been changed, and seems to be working perfectly now. We have cleaned up the IDE, and that also now appears to be working perfectly. Okay, we've seen that there was an issue with the RAM here, but a bit of reseating has sorted that out. We did boot from the ROM underneath, although that has now been removed to accommodate DFB1X. I don't have it connected at the moment, but we saw that the blue SCSI in the back there, so the SCSI port definitely was working. We have heard audio both from the onboard YM sound chip and the SDMA based digital to analog sampled sound system. So the obvious thing, actually, to be honest, we haven't tested microphone in. We haven't tested sound recording yet, which goes through this codec chip. So but obviously we've seen the output works. So that is a bit of an outstanding one that we probably do need to address. But the big standout is obviously the DSP. So this really is in a terrible state. We saw one of those pins simply just jiggling around. There's one that doesn't appear to even have a pad, and it looks like some kind of corrosion, or I don't know what's going on. Work has been done there, and it is not in a good way. So just to get an idea of what we're dealing with, what I have here is a small little program that calculates a mangled set with this by using software, by using the FPU, and by using the DSP. And if we kick that off to do a software render, so this is with a 50 megahertz 030 machine over here, 030 processor over here in the DFB1. That should work nicely. There we go, and it took 10 seconds. If we try it with the FPU, again, running at 50 megahertz on DFB1, that should take a little less. I'd guess probably 7-8 seconds. That will be, oh, actually, virtually identical. But there we go, that's a nice bit of output. Surprised by that with the FPU. The key thing is what happens as soon as I ask it to run a DSP render. Well, to my great surprise, it's doing something. I was not expecting that. Wow. Well, you can just see that I've actually just run a DSP benchmarking process, and it's all come back as working and 100%. This was failing when we ran it in the diagnostic cartridge the other day. That pin there attached to the bare trace is not soldered. This is the SRAM down here that this was also failing a test. Programs weren't executing. Is it possible that that unsoldered pin is just making good enough contact today that the DSP works? Well, potentially. I find that remarkable. And what about that pin without the pad? Maybe that's not necessary, or maybe there is just a tiny bit of pad hidden away underneath that we can't see. I was not expecting that. I was thinking this was going to be a bit of probably the hardest job to date. So that's quite remarkable. I think then what I really need to do is to get the microscope or get my loop back out onto that, have a look at the schematic and find out where those pins are meant to be going, make sure they're buzzed out okay, and that one that doesn't appear to have a pad, figure out what's going on there, and is that actually supposed to be not connected. Okay, so the first pin of concern here on the DSP, I think, is pin number 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, and that's the one here with this slightly damaged trace leading off it. But I think this one is soldered down okay. So that is an SRAM data line, and I think that leads to pin 48, to chip 48 here somewhere. There we go. Okay, so that's making a good connection, so I don't need to worry about that. Right, so the one next to it is the one I think that is not soldered. So that's pin 10. Pin 10. Ah, pin 10 is VCC. That's okay, so this is VCC, this pin here, so it's entirely possible that this doesn't actually have a connection and it still works from a different pin. It doesn't appear to be VCC. No. No, pin 11. Let me count those again. 1, 2, 3, 4, 5, 6, 7, 8. Ah, no, I miscounted. It's pin 9. Pin 10 is VCC next to it. Pin 10, right, that's the one without the pad. Okay, so that one I think is all right. So despite there being no visible pad and a little bit of wobble there, I think that has a connection. I might be half tempted just to solder a bodge wire on that anyway, as that could be running basically without one of its voltage lines. I'm not... It's buzzing out, but it could be connected internally. Yeah, I'm not sure what to do about that. Right, no, sorry, so I miscounted. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So pin 8 is actually the one that we tested and was fine. So pin 9 is the not soldered one. So pin 9 also goes to U48, I believe. Yep, there we go. Okay, so that is making a connection despite not being soldered. Is it bridged? No. All right. So I think what we need to do is to straighten this pin up. Which might require a finer tip than I have here, a finer instrument. No, actually that might be sufficient. Let me just check. Yeah, okay, there's no short there. So I'm going to go in there with a very, very gentle bit of soldering and see whether I can make that a properly connected pin again. And what to do with that VCC pin. The fact that it's measuring a short to VCC, I might be tempted actually to leave it alone and then run through a full gamut of DSP tests. So as far as I can see, I've got two options here. I either go with an incredibly fine tip and try and get in there and just touch up the one pin of concern, or I go with my normal SMD K-tip here, which is much larger and normally covers more than one pin, and trust that my flux and braid work is going to be accurate enough to keep those pins separated, given that there is no solder mask surrounding those pins. And I think on the balance of probabilities, that second option is probably the best, because I'm just not sure I'm going to make a good connection if I go in with a tiny fine little tip. So I'm going to make sure that there's ample flux in place. I'm going to make sure my tip is as clean as I can get it. Just the merest hint of solder on the end of my tip there, and I'm just going to, well, have a bit of a feel around, I think. Now obviously that VCC pin, there's no pad at all visible, so I am not doing much by reflowing that. I haven't fluxed the rest of the chip. I got carried away there. I decided to reflow that entire side and forgot to, well, I hadn't fluxed it. Now we do need to be cautious here, because I don't exactly have a supply of DSPs on my shelf. Okay. Well, I wouldn't call that elegant, but I do believe we have now made good solder contact with everything, and it seems to buzz out, so I'm going to give it a try. Well, it seems to have booted up successfully, so I'm going to have another go at running this DSP bench. Well, there we go. That's good news. What else do we have in here? We've got a DMA to DSP test. Good. Now, I believe what this does is this sends data out of the DMA, the SDMA chip, the audio data out of the SDMA chip, and samples it back in with the DSP, and it sees whether there are any discrepancies between input and output, and this just keeps running, and we get a green bar if there are no discrepancies, and any discrepancy will show up as a red line, and the border will go red. In this particular case, I'm seeing a lot of green, so well, I'm very pleased with that. So let's try something that will tax the DSP much more heavily, and this is Ace Tracker. Now the problem is this might not go well with my capture card, because I believe it sets a custom resolution. There's a very real chance we're just going to get nothing. No, okay, perfect. To be honest, this may not like DFP1. I've got a feeling that actually that has been a problem in the past. So this might be a bad test if we don't get anywhere. I've forgotten how to use this. Right, module load. Aha, we have something. Pretty much everything you hear here has been made on the DSP. Okay, so it could do all the boring stuff, but the real question is, well, can it run Doom? Well, I mean, not the computer. The computer can run Doom. We've already seen it run Doom. No, I mean the DSP. Can the DSP run Doom? So this is bad mood. This is a not a port. It's a interpretation of Doom by Doug Little. Now this work was started on this in the 90s, and it's recently probably 10 years ago, work was picked back up. So work on this actually started before the sources for the Linux version of Doom were released. So yeah, it's more of a an interpretation of how you could build a Doom renderer on the Atari system before we knew how it was done in real life. Oh dear, I'm terrible at Doom. But the key thing is that all of this, and I know this is an accelerator system, this is a 50 megahertz 030 with fast RAM, but this is perfectly capable of running on a 16 megahertz stock 16 megahertz and 4 megabyte memory Falcon, although admittedly compromises do have to be made at that point. Oh, run out of run out of guns. Oh, there we go. The key thing is that all of this texture work is done with the help of the DSP. So I think we can be quite content in saying that the DSP is certainly behaving itself, despite those slightly dubious looking pins. So I'm really quite happy with that. I don't know what I'm doing, I'm sorry. Oh, I'm getting shot at. Doom's not really my forte. I was more of a flight sim kind of a guy. I think you could probably tell that. So I was about to record my summary and go around the board here and say how I was pleased that everything now seems to be working and wrap this video up as having reached a successful conclusion. When I noticed that actually on a couple of my recent boot ups, I was getting that gibberish line back again on the IDE. It would read across the top, sort of, you know, some rubbish characters, and still don't understand exactly what's going on there. And then I got into a bit of a cycle where I couldn't get it to boot up. Let me try and reboot that. See what it says on the screen when it comes up, when the driver loads. Let me just flap around here. That's frozen. Look, the memory test. There we go. Look at that. Something going on with that cable. Now, I don't know what could cause that. I really don't. It's a brand new cable. We've seen that it has worked, and in fact, we were getting problems. Just power down there. We were getting problems with the board with no cable attached. What does it say on the HD driver as it comes up here? Yeah, look, dashed lines. I don't know if you caught that in time. I could probably try and freeze frame that. Dashed lines. Something definitely awry. So unfortunately, I can't really think of any other avenue to pursue on this IDE front, so I'm just going to reflow the back of this connector. I can't see this is going to have any difference at all, but well, as I say, there's not much else left for me to do there. IDE is fantastically simple protocol because all of the work is done at the drive end. So there's only really one chip involved, which is the COM-bell, which is the main chip that does everything. So if that's not behaving, well, how does everything else work? And there's nothing really here apart from ground data lines and one or two address lines, and otherwise it's just sort of like all signalling. So the only thing I can think of is that they perhaps are not making a great contact, or there's a subtle little bridge somewhere. Yep, no, unfortunately that's still showing up that message. Okay, now this is interesting. I've actually managed to capture an error message here on the diagnostic cartridge. This is what happens. It actually shows up if I do an initial reboot. Let's see if we can capture that. And it flies up the screen quite quickly. Didn't do it that time. Typical. And this time it passed. So we've got an intermittent fault where it shows up a memory error for what was the wording exactly? There we go. It did come up that time. It flew up the screen, and if I do that timing report, it will then fail this time. Yeah, there we go. So video counter in memory controller error at FF8201. That's interesting. So I think I've got a bit of an avenue for investigation here. Incidentally, I've done all the normal board flexing and pressing down on chips, but I wonder if we have another chip that we need to reflow. This testing has been done with a completely bare IDE header there. That is the video. That's the video chip. That's the video controller, and that is, well, that's the COM-BEL, which I think also houses the memory controller. So video counter memory controller, we could be looking at COM-BEL there. That's probably the most likely, but that is actually the video chip. So I don't know which one is responsible for that register. I'll have to go and do some research on that. We saw we had to reflow the SDMA chip over on the other side of the board there. I wonder if we might have to do something similar with COM-BEL. The problem is this is extremely fine pitch COM-BEL. That is by far the finest pitch on the board here, and you can see it's also partially obscured by my accelerator board. So yeah, I wouldn't be looking forward to that too terribly much. So I think my research needs to happen first. And I'm sorry to say, I think we're going to have to stop it there for this video. We are over an hour in, and it hasn't been, unfortunately, the great celebration that I was hoping for the end of part 3 here. As you can see, the logic analyzer is out. So, yeah, things did not have an easy fix. So I'm continuing to look into this. Not quite sure what is afoot. I've a nasty feeling the soldering iron's going to have to come back out again in part 4. But we were so close. We were so close. We had so much running. Goodness me, I had 2 different versions of Doom going and a fully featured multitasking operating system running. And yeah, now we're back to this. So sorry about that. No happy ending this time, but I will hopefully speak to you again in part 4. See you then.